Okay, so for today's question, we're going to be doing group anagrams, Leetcode 49. So the prompt says, given an array of strings, group the anagrams together. You can return the answer in any order. An anagram is a word or a phrase formed by rearranging the letters of a different word or phrase, typically using all original letters exactly once. So on the bottom we have an example. We have the words eat, tea, tan, ate, gnat, and bat. And then that's the example, the correct output. So I guess, um, what are some ways, or what's a naive way we can go about solving this problem? Or what is the more human way we would go about solving this problem? So, the human or naive way we would go about solving this problem is first, we would essentially go through every single word and we would keep track of the letter count for each word, right? So, for eat, we'd see that we have one E, so one E, one A, and one T. And then for T, we see that we'd have uh, again one E, one A, and one T. For 8, we'll see again same exact pattern. And then for nat, we'll see that A1, N1, T1. And then from bat, we'll see that B1, A1, T1. And then based off of that, we would essentially group together the the words that have the same letter count. So we would group together A, we group together eat, we group together T, and we group together um, 8. I've actually forgot one word as well. Tan, which is just A1, N1, and T again, 1. So that's one grouping. Another grouping is another grouping is tan and nat. And lastly, or the last grouping we have is bat. And now if we go back to our output, we see that that is exactly what we get. Now, doing it this type of way would be very difficult to code, and also it would just get complicated because you can imagine if you have a data structure to keep track of each each count of each word, and then so the data structure would be an array, and obviously it would be of size 26, and then you would have to go through each you'd have to compare each each collection of letter counts against each other. So as you can see, if I have this stored in a 26 in an array of size 26 with the letter count, and then I just simply compared to um to each and every possible other uh collection, then I would not only do this have to make this into a array where I keep the counts of each letter. I'll then also have to compare it against each and every other array array that I have for all the other words. And if I were to do that, I would get some time complexity that's like n being the number of words we have, k being the largest word we have, k being the largest word we have, or the size of the largest word. So it would be n squared, O of n squared um, times k, or O of n squared times k. Yeah, O of n squared times k. Now, that is a very that is a very bad not a very bad time complexity, but it's a time complexity that we can improve on. And one way we can improve on it is, instead of doing this comparison uh where we take each array or uh collection that keeps track of our count of our letters and comparing it to every other collection of counter or collection of letters, we instead what we'll do is, let's say so let's say we're dealing with the word eat. We will take this word and then we'll sort that word in alphabetical order. So we'll sort it and uh we will get uh A E T, right? Now every word we come across, we will sort into alphabetical order. And when we sort it onto alphabetical order, we recognize that when we sort even T, we'll get same A E T, and same with A T. Well, we also get A E T. We recognize that all anagrams, when sorted into alphabetical order, will give the same arrangement or the same order of letters. So we can use that to our advantage. And how can we use that to our advantage? We can essentially, once we have sorted all the letters into in alphabetical order, what we can do is store this as a key in a hash map. So we'll store this as a key in a hash map, and then we'll have the value being a list, and the list will contain essentially any word or phrase that, when sorted in alphabetical order, will give us AET. So we will then add EAT, because AET, when EAT is sorted, we will get AET, and then same thing for T, same thing for 8, and we'll keep repeating that process over and over again. So in that way, we're able to improve on the collection by collection comparison, which would give us something like n squared times k. But now um, we have improved on that. So let's first actually um, go through the entire algorithm with the test case that we have to kind of give an idea as to how it works. And then after that, I'll state the final runtime and exactly where the improvement is being made. So yeah, we have the words eat, we have tea, we have 10, we have 8, and we have bat, right? So, and then we have our hash map. So first we're going to sort eat. We get AET, and then we're going to put that into our hash map. AET, and then it's going to have the word eat. and then we see that T, we sort it, it's already within the hash map, so all we gotta do is just add it to the pre-existing list that we have. And then let's keep going forward. So now we're at 10. We get ANT. ANT is not a value within the hash map, so we add it. We add it as a key to the hash map, and the value being a list that contains the word tan. So ANT TAN. And then I should probably include the other words as well. AET, EAT, TEA. And then we finally have ATE, which is just AET when sorted. When we sort the letters into alphabetical order. So AET is already within the dictionary because we have it right here. So what we do is just we take AET and we ATE or 8 and add it to this list. So then we'll have this and 10. So this is what our hash map will look like. Eat, T, and 8. And then finally, we have bat. Bat, when we take all its letters and sort it into alphabetical order, we'll have ABT. And finally, and we don't have ABT within our hash map, so then we'll add that into our hash map, and then add a list, and then within the list we'll have bat. So this is what our final hash map will look like. So that's what our final hash map will look like. And then after that, once we have gotten to this point, all we really just do is take all the values within our hash map, add it to a final list. And then we'd return that. And again, the order of the actual words within the final output does not matter. Neither do the words within the list itself matter. The order matters. So this output is completely fine. So yeah, so exactly where is this improvement on the n squared times k time complexity made? Well, the improvement is made where uh, on the part where we are actually comparing all these collection or counters against each other. So, instead of doing some n squared sort of search to compare, um, instead what we'll be doing is we'll be doing to find the exact set or collect or uh, group the anagram or the word belongs to will be an O of 1 lookup. Why is O of 1 lookup or an O of 1 lookup? Because we are using a hash map, and essentially uh essentially what we'll be doing is we'll be taking these keys that we have right here, and then we'll be using those keys to hash um a universal key to figure out how what anagram or what word belongs to which group of anagrams. So that's where we save our time complexity on the n squared search, or the n squared runtime, the n squared k on the n squared k runtime. So instead, what we'll get is the final time complexity of our algorithm is O of n k log k, which is much better than O of n squared k. Um, again, k being the size of our largest word, and n being the number of words we can have. One other thing, so k log k essentially just represents log k because we are sorting the each word when we get it. K because before we actually oh k log k because we are sorting the word. Um, we are sorting the word before we actually do anything um to it to find out what group it belongs to, and then n just representing the number of words we have. So yeah. So, uh, essentially, what we are doing here is we are optimizing on that, and we have made it lk log k. Okay, so now let's get into the coding portion of the video. So remember, we're going to be using a hash map to um, keep our list of anagrams, or our group of anagrams. So in this case, I'm going to be using something called a default dictionary um, within Python, which is essentially just a dictionary that throws a default value uh, if the item or the key that we throw in is not found. And the default value I'm going to ask it to throw is a list. And then finally, we're going to have to loop through the strings itself. So we're going to do for word in strs. What we'll do is we'll take sorted letters. So remember, we have to take our word, take the letters, and sort them into alphabetical order. So what we'll do is we'll first turn this into a list. So in Python, if you just put a list and then around any string, it will automatically turn it into a list. And then if we do sorted, well, what this will do is it will give us back the whatever list we throw in, but in sorted manner. Now in this case, Python will just sort it lexicon graphically. And then lastly, what we're gonna do is we're going to take each letter and join it together to get our hash. And then finally, what we'll do is dictionary sorted letters dot append word. And then lastly, all we gotta do is do return. Now I'm just gonna do some simple list comprehension. Dictionary key for key in dictionary. And yeah, there we have it. If we run this, let's run it. That looks good. Submit. Yep. This is group anagrams. If anyone has any questions or any comments about the videos, please let me know in the comments. And yeah, till next time.